This is Introduction to Astro Imaging. And I already went there. Let's go to the next slide. Okay, you'll have to ignore some of these other things. Hey, I've been an amateur astronomer for more than 50 years. I got a Bachelor of Science, Physics, and Astronomy. After college, I spent 5 years as a physics teacher in the Peace Corps. I worked as a computer programmer and analyst for 35 years. I'm now retired, so I can do astronomy day and night. Actually, the astronomy I do during the day, when I retired, I bought a hydrogen alpha scope.
Oh, fun.
And the sun is fantastic. It
Wow.
changes every day. There's lots to see. And hopefully, I'll be able to show you some good
Don't
things.
really give a shit.
Um, and I've been imaging for over 10 years. Okay, this is my little observatory in Hope Valley, Rhode Island. I took a Tupperware shed and I converted it to make an observatory out of it. It's been pretty reliable. It's gone through 4 or 5 winters, plenty of storms, and it's still standing. Um, I've got a pier with a Celestron AVX mount on it, and my scopes are up there. My skies, I'm on top of a hill. They're between Bortle 4 and 5, and it's been really nice. Oops. Okay. This intro to astrophotography will be presented in 3 Zoom meetings. Okay, tonight I'm going to talk about cameras. Next Friday, I'll talk about mounts, computers, and some techniques that you're going to be using with them. And then the last meeting, what's really important is software. I'll talk about capture software and processing software. Okay, my goals for these 3 Zoom meetings. I want to give you an introduction to astrophotography. I can't teach you everything there is about it, but I can give you an introduction about it. And, one thing I got to admit these days, I think astrophotography is actually much easier now than it was 40 years ago. I did try it 40 years ago, and that was film photography. So you would buy a roll of film, there wasn't too many types available, and you put it in your film camera, connect it to your scope. You had issues of guiding. You had issue, which was very difficult, and focusing was not easy because you'd have to look through the camera viewfinder to try and get it focus process properly. Um, and then after you took your 20 photographs and filled up the roll, you'd send it off somewhere. You'd get it back a week later, and then you'd find out that maybe 2/3 of them were no good. Something happened. And but now it's very different. You get a lot of instant results. So I'm going to give you that introduction. The next thing I want to do is present the new aspects of astrophotography. It's all digital now. Hardware and software rule. And consequently, because it's digital, the results are 10 times better than ever before, 40 years ago. It's absolutely amazing when you look in the back of sky and telescope and you see what amateurs are doing. It just blows my mind. The results they're coming up with today far exceed anything that the major observatories could do 40 to 50 years ago. It's amazing and it's great. And another goal is, when you do some astrophotography and you print them out, I mean, this is the wall of my office. This is just some of my astro photos. It is very satisfying. People come over the house, I explain it to them. They're really amazed at what I'm able to do. And, after a while of working on it, you could do things like this. It's not impossible. I'm not an expert by any means in this subject. Resources, that's another great area. Things that people didn't have 40, 50 years ago. You'd have to talk to somebody else. There were some books out there, but today there are great resources for you. This is, you know, first and foremost, one thing that I really like a lot is YouTube. Okay, just get on YouTube, just type in beginning astrophotography, and you will get page after page of people who will just enjoy telling you about astrophotography. You want to learn about mounts, you want to learn about cameras. It's a great resource. And another very good resource are the astronomy equipment retailers. I just picked out this one as an example, Agena Astro products, but a lot of them do the same thing. On their website, they may have a resource section, or they may have another section, in this case, article and guides, and they will have lots of articles on filters, cameras, guide scopes, telescopes, all kinds of things. So don't be afraid to use that. A lot of them are very well written and very useful. And again, another great place is to go to the camera manufacturers. They love to tell you about their products and all the different aspects about it. So the resources are out there. It doesn't end with this little slideshow. So the first question you might want to think about is the types of astrophotography are out there and what you might be interested in. You could do a little of everything if you really want. This is a nice area, a nice simple area, nightscapes. Oh, I think about between 30, 35 years ago, there was a comet Hale Bopp, very easy to see in the sky. I actually took this picture with a film camera. You just set it on a tripod, 20-second exposure, there it is. And this one I took in my backyard maybe about 10, 15 years ago. Again, just a camera on a tripod. And there's so many stars in the sky, you can't tell which constellation it is. But this is the Andromeda Galaxy here, this little fuzzy patch. These are easy to do. This is a really nice way of getting an introduction into astrophotography. You can learn a lot just by doing these simple little things. Lunar and planetary. This is another nice little area, especially lunar photography. Lunar is very easy to do. The moon is big, it's bright, it's easy to focus. You can take short exposures. You don't need fancy equipment, cooled cameras, all these things you're going to see. It's easy to take a neat photo of it. A great way to get started. And then after you've done this for a little bit, you might want to try planetary photography, which can be very satisfying. This photo I really like a lot of Saturn. It was taken 4 years ago. You can see Cassini's division in there, which is not always easy to get. And what's always interesting when I look at the photos of the planet, it reminds me of a member of Skyscrapers who's not with us anymore. He passed away. And some of the old timers in Skyscrapers will know this name, John Hoff. He was a professional photographer. He was an excellent photographer because I'd seen some of his work. He knew a lot about cameras and film photography. And in the back of the meeting hall, right next to the door, he has a photograph there of Saturn and Jupiter. And he's an excellent photographer. And when you look at them, you see what was capable 40 years ago. And the photographs are very good, but not as good as what anybody could do today. It's very easy to get a nice photo. Film photography had its disadvantages. What's very rewarding is deep sky. When you get those big objects in there, like M42 is very easy to do, looks great. Andromeda Nebula is actually a little harder to do because it's so big. But in both cases, you're going to take longer exposures. So you have issues to think about like guiding and color. Do you want to do color or not? But it's still a lot of fun. And when you print them out, put them on the wall, it's neat to look at. Another area, an area I've gotten into because I'm retired now, is solar astronomy. This one here, the Mega Sunspot group, this was not a difficult photo to take. Uh, it just involves, you can get a special film to put on the front of your telescope. You could take these pictures, and the sun is such a dynamic object. It changes every day. You never know what you're going to see. And what was so amazing about this sunspot group is these little tiny dots would be about the size of the Earth. This is huge. This sunspot group was so big that if you took that white light filter and just put it in front of your face, you could actually see the spot without a telescope on the sun. It was so big. Um, because I've got that hydrogen alpha scope, what's really nice is you can catch some of the filaments, sunspots, a lot of other features on the sun that you can't see in a white light. And unfortunately, I can't do this. I wonder if I can. This is actually a video. This isn't just a still picture. A little disappointed that I can't do this. I wonder if there's a way. Um, I'm going to try a little experiment, see if it works.
Conrad, if you stop sharing and you go to slideshow, continue from the slide and then start sharing again, I think you might be able to do it, but I'm not sure.
Okay, the one problem is when I start my slideshow, it
Yeah.
fills up the whole screen, and I don't think I can get a hold of the Zoom. But that's a good idea. I'm going to try that. So everybody,
The Zoom is always on the top right where it says view.
okay, I'm going to say slideshow from current slide,
Yeah, yeah, there
and
you go.
then I'm going to stop sharing.
Yeah. Okay,
And
now start sharing. Now find it, start sharing, go find it on your desktop and then share.
how's that?
That's much better. Yeah.
Aha.
You
Well,
got it.
we got it. Okay, great. Great. All right. So this was the Mega Sunspot group. I already talked about it. All right. Hydrogen alpha. Okay. And this is a time-lapse photography of a solar prominence. This is a 2-hour time lapse
Wow.
compressed into about 20 seconds. This was actually about a total of 10 gigabytes of data that I had to process.
Wow.
It took me several days to do. I did this last summer, and this has been a lot of fun. Oh, this was the highlight of solar observing for me to be able to do this, and I'm hoping to do more of this. I have another one like this. It's not of a solar prominence, but it's of a solar filament. if you can see my arrow, this little dark spot down here is a solar filament. And it's like a 2.5 hour time lapse photography. And I've compressed it to about 20 seconds, and you can see the filament change. Maybe one day I'll do that as a video, as another talk, because the sun is so fascinating. It's so dynamic, it changes every day. Now, you've got those types of astrophotography. This is what I'm specializing in right now. Some people like to do photometry. They like to do searches for asteroids. I do stellar spectra. Okay, I've got a spectrograph, and a star's spectra looks really weird. It looks like this line with these dark lines in it. Okay, these are absorption lines. And the star right here, this is the star Vega, and I have software that will take it and put it in a graph form, and you can see where these dips are. And these dips actually come from the hydrogen in the stellar atmosphere absorbing light. And, there are people doing photometry, they're doing a lot of things. This could never have been done 40 years ago. It was just impossible. So let me take a little stop here to see does anybody have any questions so far? Are we good to go? All right, we're good to go. Great. All right, so I want to talk about cameras. The heart of the camera is the sensor, and I need to spend time talking about that. And what makes it so important is that when you read about cameras and sky and telescope, or you look at information about cameras on the astronomy retailers' websites, they give you a lot of details in there. What does it mean when they talk about binning or pixel size? Is this important? What should I be aware of? So I'm going to spend a chunk of time talking about the sensor. Then I want to talk about the type of cameras that are out there. A DSLR, digital single lens reflex. That's what I started off with 10 years ago. And they actually are very good for astrophotography if you have one. Within the last year, people are getting more involved with smartphones. They're not necessarily the best, but I've seen some interesting things with them. And then the last thing I'd like to talk about are the dedicated astro cameras, those expensive things you see in sky and telescope. And then the last part of this meeting, I need to talk about field of view. You have your camera hooked up to your telescope, and you're going to wonder, how much of the sky can I capture? Can I get a planet? Can I get a nebula? There's some simple formulas that you can use to help you solve that. So let's talk about sensors, and let's talk about sensor attributes. You're going to see them talk about CMOS and CCDs. This is a complementary metal oxide semiconductor. And the CCD stands for a charged coupled device. These are the two main types. I'm going to talk about the size of the sensor. Pixel size, the pixel well depth, 8-bit, 10-bit, 12-bit, how many bits the image is going to be recorded in. Another technical detail that you see with cameras is something called binning. And something that is always interesting, color versus monochrome. When I was doing my deep sky photos, I started out in color and very swiftly switched to color, monochrome. It does have its advantages. Okay, CCD chips and CMOS chips, they look like the same thing, okay? They both convert light into electrons, but CCDs are harder to manufacture. CMOS chips are easier. As a consequence, CCDs are more expensive than CMOS chips. Now, we'll talk about noise and what that is, but CCDs tend to be noisier than CMOS chips. And CCD chips require more power than a CMOS chip. So a recommendation, and I'll talk about this more later on, would be to buy a CMOS camera. Okay, it's the best buy for the money. Okay, all the cameras I use now are CMOS cameras. They cost less than a CCD. And over the last 10 years, there have been great improvements in CMOS sensors. CCDs are no longer produced, although you will see CCD cameras still available. Okay, the sensor. What does it look like? If you took a highly magnified view of it, well, it looks like a rectangular grid of pixels. You can think of an x-axis, you could think of a y-axis, and each little rectangle in here is a pixel. What's a pixel? It's just a tiny light sensor. It captures photons and it's going to convert them into an electrical signal. Now, a sensor really isn't this big. It's going to be, maybe so big. But this is just a highly magnified view. Okay, monochrome sensors versus a color sensor. Monochrome sensor is very simple, that rectangular grid of pixels. But when we go to a color sensor, it looks like this. Each pixel has either a red filter, a green filter, or a blue filter in front of it. Okay, it's going to look, if you magnify it a bit, it's going to look something like this: one red, two green, one blue. And it's the combination of these four pixels that make a single color. Depending on the strength of the red, the green, and the blue, that's where you're going to get these intermediate colors like violet and yellow and orange. Okay, the red pixels, I should say the pixels with the red filter, they only record red photons. Green, they'll record the green photons. The blue only record blue photons. Let's talk about the size of the sensor. Okay, it is measured in megapixels. You'll see that a lot. Now, a pixel array, well, along one axis, you could have 1,280 pixels, and along another axis, you could have 960. This is, a typical sensor. And when you multiply those two together, you're going to have 1.2 megapixels. Sensor size can go anywhere from 1.2 megapixels, which is on the low end. And these days you will see sensors that will have 60 megapixels. That's a huge chip. That is really huge. Another term that you're going to see when you look at the technical data is the sensor diagonal. It's just a measurement of the diagonal across the sensor. It could be in millimeters, it could be in inches. You might see a sensor that has a diagonal of 1/3 of an inch, or maybe a half, or maybe a full inch. Now, if it's a full inch, you're getting to a bigger sensor. Another technical detail that is important is the pixel size. It's the size of the pixel in microns. Okay, a micron is 1/1000th of a millimeter, so it's pretty small. This little symbol here is the symbol for a micron. So you might see something like 2.3 microns to 9 microns when they're describing a camera, how big the pixels are. These are very common sizes. For deep sky astrophotography, larger pixels are preferred. You're going to capture more light. For planetary imaging, smaller pixels are preferred so that you can get more resolution. Planets are much brighter, so you don't need to expose things as long. My camera is 4.6 microns pixels, and it's something in the middle. I just found that very useful. Okay, another specification about pixels is something called the well capacity. You can think of pixels as buckets, and it's a measure of how much light the pixel can absorb. Okay, and you might see values anywhere from 15,000 E to almost 64,000 E. A higher capacity means that you can take a longer exposure before the pixel gets full. Again, think of each pixel like a bucket. When the bucket is full, that's it. It's saturated, no more collecting. Does that make a difference? Well, suppose this bucket is collecting the photons from a star. And suppose this bucket is collecting photons from a nebula near the star. So when this bucket is full, because the star is brighter than the nebula, okay, it stops. But nebulas being fainter than stars, so this bucket is still collecting. So what that's going to do, the contrast between the nebula and the star won't be quite right. Let's talk about the bit. Okay, when you take an image, the electrical signal in each pixel gets converted to a number. The bit depth is the possible range of numbers that's going to get assigned from that pixel. Now, 10 years ago, when these cameras first came out, you would see a lot of 8-bit cameras. So that electrical signal from each pixel would be converted to a number from 0 to 256. And then, as 10-bit cameras came out, it went from 0 to 1,000. And today, you will see a lot of 12, 14, and 16-bit cameras. Okay, a 16-bit camera will record that number anywhere from 0 to 65,000. Now, what's the big deal with all these numbers? When you have a higher bit depth, for example, 16-bit, 0 to 65,000, it produces smoother graduations between areas of varying brightness. With an 8-bit, those steps are going to be much more coarse, and it won't be as smooth. Let me take a little stop for a moment. Does anybody have any questions?
Yeah, I have a question, Conrad. I never really understood bit depth and the wells and all that. You explained it really well. How does when the bucket is full, it gets emptied out and then more electrons? Can you explain that
No.
process a little better?
When the bucket is full, I'll go back.
Yeah.
Oops. Right, how you going?
I'm really happy the CMOS chips
When
have
the-
surpassed the CCDs now.
When the bucket is full,
Yeah.
that's it. It stops collecting.
Right.
No more. but all of the buckets around it that aren't full will keep collecting. You know, if you took an exposure, now this is a real exaggeration, of something like, let's say, an hour, all the buckets would be full, and all you would get is just something that's all white.
Okay.
You wouldn't get anything. Okay? The bucket doesn't stop, it doesn't empty out and start again. It's just
Oh.
full. That's it. No more.
Oh, okay. So it's in varying degrees of being full and empty, right? Oh, okay, at any given time.
Yeah.
And basically, that's when you adjust the gain on your
Well, you might,
or
well, there's
exposure.
several ways you could handle that. Yes, you could adjust the gain, or you could adjust your exposures. I'll be
Right.
talking about frame stacking, not today, this meeting, but either probably in a couple weeks.
Okay.
But you know, you could actually do shorter exposures and then you stack them all together. Okay. And all that stacking process is done in the software.
Yeah.
Okay. Not on the camera.
Oh, okay. All right. Thank you.
Okay. Let's see. Okay. Another feature, technical feature about sensors is this feature binning. And we're going to combine adjacent pixels to make a super pixel. Okay, so here's a situation where I have just one pixel that's called bin 1. If I do a bin 2, I take 4 pixels and I make a super pixel out of it. Bin 3, I've never used this before. You take 3 pixels and make a super pixel out of it. What this does, it increases the signal to noise ratio. So suppose this captures 50 pixels right here. But if I had 4 pixels that captured 50 photons, then I would get a total of 200 for the super pixel and make it a little brighter. The only problem with binning is that it decreases the resolution. And it is useful because you can gather light for faint objects. And so it's good for framing and focusing. You know, if you're trying to frame a galaxy, and it's all galaxies are faint. A lot of nebulas are faint when you first look at them. You want to get as much light on that sensor and so that you can look at it and get your nebula or galaxy right in the center. You know, if you have a planet, it's so bright you don't have to worry about something like that. Which is better, color or black and white? Interesting question. I've got a picture here of Barnard's Loop. Now, does anybody know what constellation this is?
Orion.
There you go. All right, here's the belt of Orion. Here's the sword, the legs to it. Orion Nebula. Here's the Flame Nebula. A teeny tiny dot here. I don't think you can see it. It's actually the Horsehead Nebula. But Barnard's Loop is this interesting ring right here. I always wanted to take a picture with it. So I used my DSLR. I hooked it on a telescope. I took a picture. I took a color picture of it, and I had an awful time trying to get the colors right, and I never could get them right. You can see it's much too red here. I've got green in the background. It's very difficult. Color is certainly much prettier than black and white, but it is a lot harder to process. You have a lot of things to take into consideration. Interesting concept, something called white balance. What do you want in here to be white? Now, this star up here should not be white because it's a red giant. This star down here shouldn't be white because it's a blue giant. So you got to figure out, what colors the stars should be. And a lot of things you're going to be adjusting in there with color. You have things like hue and saturation. You've got three colors here that you've got to adjust. If you put too much red, does it look good? Not enough green? It's really not easy. But that doesn't mean you shouldn't try it, because with some objects, like the Orion Nebula, this came out very well. And I really like this photo. And you can do great color photography. Some are going to be easier than others. Okay. And one last attribute of sensors is something called noise. You see that a lot. You have to remember, these are sensitive electronics. Okay. And technically, noise are electrons in the pixel that don't come from light. They're measured in electrons per pixel. You might see something like this, 1.2 E or 4 E with a negative sign per pixel. Obviously, lower is better. You want as little noise as possible because it throws your image off. It's generated in the camera's electronics. Not much you can do about it. Even in total darkness, there is noise in the camera electronics. You'd be surprised. If you cover up your telescope and you take a 30-second exposure, you'd be surprised what you see on there. Warmer temperatures generate much more noise. However, cameras can be cooled to counter the effect. And actually, with the noise that gets generated in the sensor, you can remove a lot of it in the processing phase. There are ways of doing it. It's part of the techniques, new techniques that you have to learn. In the old days, the noise would have been called graininess in film photography. Okay, now I'd like to talk about cameras. Okay, the type of cameras, DSLR, smartphones, and the dedicated Astro cameras, both the cooled and uncooled. Here's my first Astro camera. It was a Canon Rebel T1i. It had a 15 megapixel color sensor in there. It was 22 millimeters in this direction by 15 millimeters in this direction, which is actually a pretty good size sensor. You can just take a camera like that with the lens on it and put it on a camera tripod, take pictures. You can connect it to a telescope, but you need some attachments for it. The first attachment is called a T-ring, and this is what it looks like for a Canon camera. You take the lens off, and then you're going to connect this to the camera. Okay, this part connects to the camera, and then if you notice, it's threaded on the inside here. The next part you need for it is called a T-mount adapter, 1¼ inch, because this is going to go in your eyepiece holder. This part is threaded, and this can actually screw right in to the T-ring. And when it's connected, it looks like this. I can connect this to a telescope now. And one thing I'd like to add to it, a very useful accessory is a camera remote. I bought one for the camera, that way I don't have to touch it. Because if you touch it to flip the shutter, you might move the camera. This is the eyepiece holder on a Newtonian scope. The Newtonian scopes typically don't have enough eyepiece travel to accommodate a camera like this. But one way you can adjust for it is, if you're brave, you can drill some holes and move the telescope's mirror forward a couple inches. And I've done that before. Or what you could do is you could get a Barlow lens, which actually pushes out the image a bit. But that would also increase the focal length of your telescope. But both of those would work. One thing I've noticed, because I've owned a few refractors over the years, is that refracting telescopes usually have enough travel, not only for the eyepiece, but also you can take the eyepiece out and put a camera in there, no problem focusing. Okay, smartphone adapters, kind of funny looking gadgets where you connect your smartphone to it and you can connect it to the eyepiece of your telescope or any other optical instrument for that matter. And some of them I noticed have Bluetooth remote controls on them. That way you don't have to touch the smartphone in order to click a picture. Smartphones, they amaze me. They vary so much in their ability to capture images. My little smartphone was only $100. I just bought a cheap smartphone. I only use it once in a while. But there are smartphones out there that cost $1,000. They're really expensive and they can capture some nice pictures. But they're really not designed for astrophotography. They can photograph bright objects like the moon fairly well, but not deep sky objects fairly well. In low light, I've noticed that images are not real sharp and colors don't come out real well. An interesting story about a smartphone. A couple years ago, on a Saturday night at Seagrave, when we had an open house, I was at the 16-inch, and this little girl came up with a smartphone. She put her smartphone close to the eyepiece of the 16-inch and took a picture of the moon. And that was really interesting. And she probably took it to school next week and showed all of her friends. Let's see. Yes. Does anybody have any questions about smartphones or digital single lens reflex cameras?
Conrad, are mirrorless cameras coming into the mainstream for astrophotography?
Yes, they are. I know Sony has put out the mirrorless cameras, and they are very nice. There's a couple nice features about them. One, they don't weigh as much, and they are very good. And, they are fairly new. I don't know if some of the software has caught up with them, but they would make a great choice also as if you want to try using one of those cameras. As long as you can take the lens off, you can do a lot with it. Let's talk about dedicated Astro cameras. Okay, you see these in, Sky and Telescope, Astronomy magazine. You go to the Astronomy retailer website, they're plastered all over the place. One of the big features about these type of cameras is they require capture software and a computer, okay? Software to capture the image is not built into these things, okay? I went to one website and I counted 191 Astro cameras for sale. I was amazed. I couldn't believe it. And they went from a low of $130 for this one, all the way on up to $24,000 for this one. So the prices are all over the place. Mind you, this is a nice camera. Don't doubt me about that. It is confusing, but there's a few important things that I want you to know. There's only two big sensor manufacturers, Sony and Kodak. Okay, Sony done a great job making Cmos sensors. Kodak, a great job doing the CCDs. So you will see the same sensor being used by different camera manufacturers. For example, QHY is one company and ZWO is another company. Their 53462C it uses the exact same chip as this ASI 462. You know, they may be very close in price. Sometimes the camera manufacturers might add a few other bells and wheels to it. They might add some other additional adapters. Another feature some of them like to add to it is additional memory that they'll use for buffering. Okay, if you're using your camera on a high-speed mode and it's taking pictures once every, 5,000th of a second, that image will go into the buffer and the buffer will then feed it into the computer as fast as it can. This is important to know. An expensive camera is no guarantee of great results. It doesn't hurt, but it's not a guarantee. A lot of this has to do with image processing. You can take an average camera, do some great image processing, and come out with a wonderful image. Cooled cameras. You'll see a lot of cameras out there, advertising that they're cooled. They do have built-in cooling units. The chip, I should say, or the sensor can be cooled 35 degrees Celsius below the ambient temperature. And this reduces thermal noise. It does improve the image on hot nights. I noticed I've got several cameras. One of them I bought years ago that wasn't cooled, that during the summer there was a lot more noise in the camera. Images were not as sharp. I did buy a cooled camera a couple years ago. The only issue with cooled cameras, they're going to add to the cost. Okay, at least $400 to $500 or more to it. Does anybody have any questions about these dedicated Astro cameras? Okay, only another 2 hours to go, and we'll be done. Okay, finally, I want to talk about field of view. How much sky can your camera and scope cover? Okay, if you had a digital single lens reflex and you had your 50mm lens on it, you're going to get a big chunk of the sky. Nice big chunk of the Milky Way, looks really good. And if you took that same camera, but you put a 200mm lens on it, you just get a little spot. You would get a great photo of this nebula. So there are two factors in the calculation for field of view: the size of the sensor and the focal length of the scope. And it's actually pretty simple. So let's do a field of view calculation. Okay, one thing we need to know is the size of the sensor in millimeters. I'm going to use an example. This is a ZWO ASI 120 camera. It's not a big camera. The size of the chip, the sensor, is 4.8 millimeters. And we're going to assign that to a variable D. The second part of the equation is the focal length of the telescope in millimeters. So if you have a Celestron C8 Schmidt-Cassegrain, the focal length is 2032 millimeters. We're going to assign that to a variable L. We're going to use this formula, 3400 times D, and we're going to divide that by L. Okay, and this is going to give us the field of view in arc minutes for the telescope and the camera. So 3400 times the 4.8 millimeters, size of the sensor, and then we divide that by the 2032, okay, that rounds out to about 8 arc minutes of the sky. And I'll explain what that means in the next slide, what that means. Okay, so what could you image with that type of a field of view? Well, if you had the planet Jupiter, which is about 1 arc minute, that would fit in there. If you had M57, the Ring Nebula, that will fit in there very nicely. If you had the Whirlpool Nebula, that's getting a little too big and you're going to cut off part of it. It might, not all of it's going to fit. If you had the moon, which is 30 arc minutes, well, you're only going to get a piece of it in there. Something like the Andromeda Nebula, no, that's a big object. It's 180 by 60 arc minutes. That's just not going to fit. Is there anything we could do? Well, let's go to the next slide and see. So let's change the telescope. I'm going to use that same camera, and the size is 4.8 millimeters. Okay, that's my D. I'm going to now use an Astrotech 70 millimeter f6 refractor. I picked that because that's what I have. I do have one. The focal length is 420 millimeters this time. It's a lot less. I'm going to call that L. We're going to use the same formula. So 3,400 times 4.8 divided by 420. We're going to get 39 arc minutes of sky. That's almost 5 times bigger. Okay, that gives us a lot more possibilities. When it comes to the planet Jupiter, that's, it's going to end up as a tiny dot on the camera sensor. That doesn't work. Something like the Ring Nebula is still going to be pretty small. Now, there are some planetary nebulas that are bigger. For example, the Dumbbell Nebula, M27. That's a lot bigger. That would fit on it and look good. The Whirlpool Nebula is going to fit on it very nicely, and you'll get a great photo for that. The moon is going to fill up the sensor. You're going to get great photos of the moon. But it's still not big enough for the Andromeda Galaxy. You're only going to get a little piece of it, and you won't like it. Okay, let's try changing something else. Let's try changing our camera. Okay, this time I'm going to use
Conrad, I have a
Yes,
question.
sure.
Is the diameter across or is it diagonal this way? You know what I'm saying? Let me see.
We're talking about the formula?
Yeah, the formula.
Okay.
Like, is it this way straight when you measure the
Okay,
when you
could
measure
think of
the
this-
chip, or is it like going diagonal?
Okay.
The diameter.
Think
You
of
know what I
this
mean?
as the x-axis. Okay,
Yeah.
I'm going 22 millimeters along one side of that rectangle. Okay, do you understand that, Greg?
So what
It's not
would you say?
across the diagonal. It's
Oh, it's
across,
the
let's say it's across the bottom of the sensor, that part of the rectangle.
Oh, okay. So it's straight then.
Yeah, it's
It's not-
straight. It's not the
Not
diagonal.
like the LCD TVs that you buy, they always give it diagonal because it sounds
Yeah.
bigger. 75 inches. It's not 75 this way.
Yeah.
By this way, it's 75 diagonal. All right. So this way it's straight across. Okay, thank you.
All right. Okay, I'm going to use that same telescope, my little Astrotech. 420 is equal to L. We use the same formula. And so 3,400 times 22 divided by 420. That gives us 178 arc minutes. Now we're getting big. And you can see where this is leading. This is 20 times bigger than the very first case when we started. So what can we image? Oh, planets? No. Planets will be just little teeny tiny dots. Planetary nebulas are too small. The Whirlpool Nebula, well, you know, it's only going to fill up maybe 1/10 of the chip. So it's actually going to be pretty small. The moon you could image. It's also going to be small. It's going to take up 1/6 of the chip. But you will be able to get the Andromeda galaxy on there. And in fact, that's the combination that I used in order to take this picture. I used my DLSR on my little Astrotech, and I also added a field flattener because that's a big field of view, and it came out very nice. Let's talk about field of view, the size of the sensor and the focal length. So I've got a little graph here. Okay, on the y-axis, small field of view here, large field of view going in this direction. And we're going to look at the focal length of the scope, and I'm also going to graph the size of the sensor on this one graph. And as we go in this direction, the values are going to increase. So when it comes to the size of the sensor, okay, small size of sensor, small field of view. As it gets bigger, okay, then we're going to have large fields of view. But with the focal length of the scope, we have just the opposite happening. When the focal length of the scope is small, you get large fields of view. And as the focal length increases, we get small fields of view. Okay, so you kind of have to work these two together depending on what it is that you want to take a picture of. Now, once you buy your camera, you're kind of stuck with that one particular sensor. But you know, there are things you can do with your telescope to adjust the focal length of it. You know, for one thing, if you want to increase the focal length of your scope, you could always add a Barlow lens, which could double it or triple it. So if your scope had a short focal length, you could put a 2x, a 3x, maybe even a 4x Barlow on it if you wanted to take a picture of that planet. But if you had something like a Celestron 8-inch Schmidt-Cassegrain with a 2000 millimeter focal length, and you wanted to take a picture of a galaxy, and you can reduce the focal length of it using something called a focal reducer. You see a lot of those out there, and that'll take it and shrink it and give you a bigger field of view. So you do have options to yourself there. So as a general rule of thumb, planets and planetary nebulas are small. So you're going to need a telescope with a long focal length if you want a good image. So you can use Barlow lenses to increase your focal length if your scope doesn't have a long focal length. You know, globular star clusters are kind of in the middle between planets and big nebulas. So, you know, a focal length in the intermediate range. You know, if you had a Celestron CH Schmidt-Cassegrain, that would be a good size for that. Nebulas and galaxies are large, okay? Not all of them, but a lot of the neat ones are large. So you're going to need a telescope with a short focal length or camera with a big sensor. Now, this could get real expensive, so I'm not going to recommend that. But you can always take your telescope, put a focal reducer on it, and shorten the focal length. Okay, so just some last thoughts about this, and then we're done. Okay, if you have a digital single lens reflex, you know, I'd encourage you to use that. You already have it. You can get some adapters to it, or you could try nightscapes. You know, you can attach a 300 millimeter telephoto lens to it, and it's going to behave like a small telescope. And you could do some great photography with that. There are some great telephoto lenses out there. And just make sure you get a remote for it to control it. But if you want to buy a dedicated Astro camera, and I had to think about this carefully, because I don't want you to spend a fortune at this introductory phase. You know, I feel like I could recommend it's a ZWO ASI 120. I have a couple cameras from this company, and their cameras have been very reliable and pretty good value for the money. It's not too expensive. It's $180. It's monochrome, it's not cooled, and it's only 1.2 megapixels. And you see a lot of them out there on the Astronomy retailer site. For some strange reason, and I don't know why, color cameras cost less. You can buy a camera from this company. It's an ASI 120, but it's a color camera, and it's $150. If you really want to get into color. And, you know, don't be afraid to utilize a focal reducer or a Barlow lens to work with your camera so that you can, you know, just get a good field of view for the object that you're interested in. That's it. And I know we got off to a slow start, but we're off and running. And, you know, thank you very much for attending. I hope this was useful. And this is just the first one, okay? And next week we'll talk about mounts. We'll talk about some techniques. And so does anybody have any questions? Any questions out there? You know?
It's not a question so much as a statement that I feel like I have a much better idea of the concept of a focal reducer and how useful it is and why so many people use them in astrophotography. That now I get it. Thank you.
Oh, good. Well, I'm glad you got something out of it.
Oh, I got a lot.
Oh, yeah. They are useful. I don't know if any of the scopes at Seagrave have one. You know, Barlow lenses are pretty common. People have been using Barlow lenses, I mean, ever since I was a kid. You know, instead of buying more eyepieces, you'd get a Barlow lens. But focal reducers, you know, ever since, you know, we get into this CCD and Cmos cameras, focal reducers have become pretty necessary because people want to do astrophotography and they want to get more on that camera chip.
Conrad, is there any advantage of using a telephoto lens over a zoom lens? I'm not quite sure the distinction there.
Well, you know, telephoto lenses and zoom lenses have a lot in common, okay? Like, for example, a telephoto lens, you could buy, let's say, like a 200 or a 300 or a 400 millimeter telephoto lens, okay? The focal length of that lens is fixed, okay? You can't change it. A zoom lens, like you could go from, and I have several zoom lenses, you could go from 100 to 300. The fixed telephoto lens is probably optically a bit better than a zoom lens because there's no moving parts in there to worry about. But if you have a zoom lens, and I've used zoom lenses before, you know, don't go out and buy another lens. Use your zoom lens. Take advantage of what you have before you go out and spend money because you'll learn from it. And if you really want to go out and buy that $1,000 telephoto lens, go ahead. But play with your zoom lenses now because it's a good learning opportunity. Are we good to go? How's everybody out there? Okay,